is overwhelming, its true nature remains one of the biggest mysteries in modern astrophysics. Scientists are constantly developing new theories and experiments to try and pin down what this elusive substance is made of and how it interacts with the universe around it. One leading candidate for dark matter is a hypothetical particle known as a WIMP, or weakly interacting massive particle. WIMPs are thought to be particles that interact very weakly with ordinary matter, making them difficult to detect. A black hole begins its life in the most dramatic way possible, the death of a massive star. This cosmic event is one of the most powerful and awe-inspiring phenomena in the universe, marking the end of a star's life cycle and the birth of something entirely new. When a star much larger than our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse. This process is triggered when the star can no longer sustain the nuclear reactions that have kept it burning for millions or even billions of years. Gravity, no longer countered by the outward pressure from nuclear fusion, takes hold and the core of the star implodes. The immense gravitational forces cause the core to shrink rapidly, leading to an intense increase in temperature and pressure. This collapse can lead to a supernova explosion, an event so luminous that it can outshine an entire galaxy for a brief period. The energy released in a supernova is so vast that it can briefly rival the brightness of all the stars in the galaxy combined. The core that remains after the explosion, if sufficiently massive, will continue to collapse under its own gravity, forming a black hole. This remnant, now devoid of its outer layers, becomes an incredibly dense point in space. This newly born black hole now possesses a gravitational pull so strong that not even light can escape from it. The gravitational forces are so extreme that they warp the very fabric of space and time around the black hole. The boundary beyond which nothing can return is known as the event horizon, a point of no return. Once anything crosses this boundary, it is inexorably drawn into the black hole, never to escape. The birth of a black hole is not just an end, but a beginning, one that unfolds in the dark recesses of space, a place where the laws of physics stretch to their limits. It is a realm of mystery and wonder, where our understanding of the universe is constantly challenged and expanded. A black hole is more than just a point in space. It is a complex structure with distinct regions. At its heart lies the singularity, a point where gravity is infinitely strong and space-time curvature becomes infinite. Here the known laws of physics cease to function, and our understanding of the universe breaks down. Surrounding the singularity is the event horizon, the spherical boundary beyond which nothing can escape. The event horizon is not a physical surface, but a mathematical boundary. Once anything, be it matter or light, crosses this threshold, it is irrevocably pulled towards the singularity. The radius of the event horizon, also known as the Schwarzschild radius, depends on the mass of the black hole. For a stellar mass black hole, this might be a few kilometers, while for a supermassive black hole, it could span millions of kilometers. Black holes are renowned for their extraordinary gravitational pull, which warps both space and time. According to Einstein's theory of general relativity, massive objects like black holes create deep wells in the fabric of space-time. This warping effect is what we perceive as gravity. Near a black hole, these effects become extreme. Time itself slows down relative to an observer far away from the gravitational source, a phenomenon known as time dilation. As an object approaches the event horizon, this time dilation becomes more pronounced. To a distant observer, it would appear as though the object slows down, asymptotically freezing in time just as it reaches the event horizon. However, from the viewpoint of the object itself, it crosses the event horizon and continues inward in finite time. This discrepancy arises because the warping of space-time affects the passage of time differently depending on the observer's position. Black holes are often depicted as insatiable cosmic predators, devouring anything that comes too close. This process of feeding is both violent and spectacular. Material from a surrounding star or interstellar medium can fall into a black hole, but not in a straightforward manner. Before being consumed, this matter forms an accretion disk, a rotating disk of gas and debris that spirals inward, gradually losing energy and angular momentum. As matter in the accretion disk moves closer to the black hole, it heats up due to friction and compression, reaching temperatures of millions of degrees. This hot, glowing disk emits vast amounts of electromagnetic radiation, particularly in the form of X-rays. Observing these X-ray emissions allows astronomers to infer the presence and properties of black holes, even when they cannot be seen directly. The question of what lies inside a black hole beyond the event horizon is one of the most profound mysteries in astrophysics. Theories suggest that at the very center of a black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. Here, space-time is curved to such an extreme degree that our current understanding of gravity and quantum mechanics cannot describe what happens. One of the biggest challenges in understanding black hole interiors is the clash between general relativity and quantum mechanics. General relativity predicts the existence of singularities, but quantum mechanics suggests that such infinities should not exist. This tension hints at the need for a new theory of quantum gravity, which would unify the principles of the two frameworks and provide insights into the true nature of singularities. Black holes have long captivated the imagination, not just for their destructive power, but also for their potential as cosmic gateways. Theoretical physicists have speculated that black holes could be connected to other regions of space-time via wormholes, hypothetical tunnels that might link distant points in space and time, or even different universes. These ideas, while speculative, have intriguing implications for our understanding of the cosmos. A wormhole would consist of two mouths connected by a throat. If traversable, it could allow for faster-than-light travel and even time travel. However, such wormholes, if they exist, would require exotic matter with negative energy density to remain stable and prevent collapse. While no evidence for such matter exists, the idea of wormholes remains a tantalizing possibility in the realm of theoretical physics. Black holes are not mere cosmic vacuum cleaners. They play a crucial role in the formation and evolution of galaxies.